Hello, in today's lesson we are going to be looking at the very last topic of the chemical analysis subtopic, which is chromatography. Our learning intention for this lesson is to explore a qualitative analytical technique called chromatography and practice some examples of problem solving type questions which are most often asked. Our success criteria are to explain what chromatography is and what it can be used for, to calculate RF values, that's retention factor values for different substances, and to answer some problem solving questions. So first of all, what is chromatography? Well, it's an important analytical technique because it allows chemists to separate substances in complex mixtures. There are a variety of different types of chromatography which are used for different things in different contexts. In the school lab, it is a qualitative chemical analysis technique, which means we are looking at what is present in a substance or compound or mixture, but we can't necessarily quantify each of the different substances present. The first type we're going to look at is paper chromatography. So when substances are separated, this is when they travel in a mobile phase, which passes through a stationary phase. So in paper chromatography, which I'm sure everybody's done before lower down the school, your piece of paper is your stationary phase. It is like it sounds, it stays where it is. The mobile phase is going to be the material, like the solvent. Sometimes we use water, sometimes we use ethanol, sometimes we use mixtures, and that is going to travel up the paper. Now that's why it's called the mobile phase, because it moves, it travels up the paper, and with it, it will separate the different substances out based on one, how big the molecules are, and two, their polarity as well. So that is how they are able to separate substances. Think about it like ink in a pen. In a black pen, if you do a little dot and then carefully lower your paper into a solvent like ethanol or an ethanol and water mixture, then what happens is the inks, the different coloured inks in the pen, start to move at different speeds. You sometimes get some pinks, some blues, some yellows. So lots of different colours make up black ink. So that's quite an interesting one to do. The second type of chromatography is thin layer chromatography, shortened to TLC. It's very similar to paper chromatography, but we don't normally do these in the school lab. Instead of paper, the stationary phase is a thin layer of an inert substance, so something that's not going to react with anything in the mixture, like silica. And that is supported on a flat, unreactive surface. So again, we don't want anything reacting with our mixture to be separated, so it's put on a glass plate. TLC does have some advantages over the kind of normal paper chromatography. The mobile phase is going to move more quickly through the stationary phase. Sometimes you can be waiting a while when you do paper chromatography for your solvent to travel all the way up the paper as far as you need it to go. The mobile phase moves a lot more evenly. I think a lot of people will remember, if they've done paper chromatography before, that sometimes you don't get good separation of the different components because the mobile phase, being a solvent on a bit of paper, doesn't really move that evenly through. It shows a greater separation, so like I just said, of the components in the mixture. So it's going to be a lot easier to analyse. If the different dyes, for example, in an ink, the different colours are further away from each other, then it's going to be more easy to analyse. If they're kind of clogged together, sometimes you get colours on top of each other and it's not as easy to analyse. The last type of chromatography we're going to look at is gas chromatography. Now that is something that you will go on to look at if you go and study chemistry at university, and this is used to separate really complex mixtures. It is much, much better than thin layer or paper chromatography put together. It's because it's more sensitive, so look at all the different parts of the machine. It is far more complicated and advanced than paper or thin layer chromatography. And it can not only tell you what chemicals are in your mixture, but also how much of each chemical there is. So GC can be used for lots of different things. For example, racehorses are sometimes have their urine tested to make sure there are no chemicals in there that shouldn't be. That would be something you could analyse with GC. So the mixture to be analysed is injected, so you only need very small amounts of the liquid, into a stream of carrier gas. So that's what you can see here, and that's where the wee sample injector is, where you inject your substance. It then passes through this column here, which is just a thin tube, and that separates it into the different substances. This is much nicer than paper or TLC because you get a nice readout, which is a chromatogram, and it shows you the different peaks for your different substances at their different retention times. So it's far, far easier to use. So we have to have a good understanding of how to calculate RF, or retention factor values. When we get a very visual result when separating our coloured inks on paper or thin layer chromatography, the spots can look quite similar and it can be quite difficult to analyse, like I said earlier. So what we can use is this thing called the retention factor, and it can be calculated to identify the components, because every single one will have a different value. So every different compound will have a different RF value. It will travel a different distance than other components. So how we do this is the retention factor is calculated by taking the distance travelled by the spot, so that would be from your starting line to where your spot finishes, divided by the total distance travelled by the solvent. So remember, your solvent starts at the bottom of your paper and goes all the way up to the top. So here is an example of how to calculate RF values. So our solvent is going to travel a total of 6.5 centimetres, and we have a red dot here contained within this ink and a blue dot. The red dot's distance is 2.5 centimetres away from the origin line, which remember we draw in pencil, and the blue dot is 5.2 centimetres away. So very, very straightforward. And calculating the red dot's RF value, we can do 2.5 divided by 6.5 to get a retention factor of 0.38. Now there are no units for this because it's like a kind of ratio, if that's a helpful way to think about it. To calculate the blue dot, we've got 5.2 divided by 6.5 and we get 0.8. So very, very easy, very straightforward to calculate retention factor. Now, what you'll sometimes see is, or what I'd like to just take you through is an example where you actually have to measure the dots by yourself. So if this was on paper in front of you, what you could do is get your ruler out and do this yourself. Now remember, it is a ratio that we're calculating here. So the actual distances might be different from person to person, depending on if you're looking at this on a screen, on a piece of paper, but the ratio values should be the same. So what I did was I measured this on the screen with my ruler, and I have a distance the solvent travelled of 10.2 centimetres. The red dot was 2.1, the blue dot was 5.3, and the green dot was 9.8. So what I want you to do is I want you to pause the video, go and calculate the RF, the retention factor values for the green, blue and red dot, and then unpause the video and check over your answers. Hopefully you managed to do that okay. We have for the green dot 9.8 divided by 10.2, which gives 0.96. For the blue dot, we have 5.3 divided by 10.2, which gives 0.52. And 2.1 divided by 10.2 gives 0.21. So here are a couple of kind of things to think about when you're faced with problem solving questions. So here is the chromatogram that you would get out of a typical gas chromatography detector. This is the strength of response versus time. So as time goes on, the compounds are separated by their retention time, and the strength of response here is measured, as you can see, by the kind of peak size. So what we can gather from this, here is a couple of things to think about. Substance A, so that was the very first substance, is present in the smallest quantity. Now that's not because it has the shortest time, that's because it has the smallest peak. So the kind of area under the peak can be used to determine the concentration of each substance. So A is the smallest, which means it is present in the smallest quantity. Substance A also has the shortest retention time, so that means that it separated much quicker than any of the other substances. Substances B and C, because they have the same height of peak, they are present in equal amounts. So there are equal amounts of B and C. How do we know that B and C are not the same compound? If they were the same compound, they would have identical retention times, and they don't. Their retention times are very close together. As we can see, we've got a little bit of overlap here, but they are definitely different compounds. Substance F has the longest retention time, and it also is present in the greatest quantity, so it has the largest concentration because it's the largest peak. Let's practice some questions then. Question number 1. Now, these questions in chromatography are always very long. Because they're problem solving, they do tend to give you lots and lots of information to read through so that you have a good amount of background before you answer the questions. So we'll read through the questions. As always, give the questions a little go by yourself and then unpause the video and self-mark your answers. So the maturing process in cider samples can be monitored using TLC. We've got samples of lactic acid, malic acid, and ciders A, B, C, and D spotted onto a silica plate, and the solvent was allowed to travel up the plate. Now, it tells us in this diagram here that the distance moved by the solvent was 16.4 centimetres. The retention factor, as we know, can be calculated by taking the distance moved by the substance divided by the distance moved by the solvent. Question A is asking us to calculate the RF value of malic acid. So if we look at this table here, we have a distance travelled by the malic acid spot of 4.1. So to calculate this, we're going to do 4.1 divided by the distance moved by the solvent, which was 16.4, and that gives us a value of 0.25. So the RF value for malic acid is 0.25. Now, part B says the maturing process is complete when all of the malic acid has been converted to lactic acid. So that's when we know that the cider is ready to be bottled, when there is no more malic acid and we only have lactic acid. We have to use the chromatogram to determine which cider is ready to be bottled. Okay, so what basically we're looking for here is we are looking for one of the spots that doesn't have any malic acid in it. It's only got lactic acid. So what we are looking for then is we are looking for a spot that only has a distance of 8.2 and doesn't have a spot where 4.1 is. So if we look along here, 1 is the lactic acid, so it's not that. 2 is the malic acid. 3 has 2 spots. 5 has 1 spot at the malic acid. 6 has 2 spots. 4 is the only one that has 1 spot at lactic acid. So it's going to be cider B because it has that value at 8.2 only. So question number 2 then. Essential oils from the lavender plant are used in aromatherapy. Gas chromatography can be used to separate and identify the organic compounds in lavender oils. So chromatogram 1, which is this chromatogram here, is lavender oil A. We are told that the relative concentration of each component can be calculated using that formula. So relative concentration equals the component peak area, so the peak area of the component we're looking for, divided by the total peak area and then multiplied by 100. Part A is to calculate the relative concentration of linalool in lavender oil A. So we look for linalool. We say, right, our component area is 31,909. Our total peak area is 79,310. If we divide those by each other, multiply by 100, we get 40.2%. Part B, calculate the relative concentration of linalool and lavender oil A we already did before. Part B is different varieties of lavender oils have different compositions. Identify the compound found in lavender oil A that is not found or missing from lavender oil B. So this is a chromatogram from B. So we've got 1, 2, 3, 4, 5 peaks on B, but we have 6 on A. So what we need to do is look for where is the missing peak. Now, this doesn't necessarily mean that the peaks need to be the same heights. They need to just be in the same places. So if we have a wee look at the time on the chromatogram and the time on this chromatogram, it's looking like there's something missing here. So between 20 and 22 minutes, we should have two peaks. One is before 21 minutes, one is after 21 minutes. So let's look and see. Here we have the one before 21 minutes, but we don't have the one after. So the answer to this is 5, which is geranyl acetate. 3. Paper chromatography is often used to analyse the mixtures of amino acids produced when peptides are broken down. This is some Unit 2 knowledge coming in here. On a chromatogram, the retention factor for a substance can be useful for identifying the substance. Again, usually you are given this equation when they want you to use it. The structure of a pentapeptide, so that's 5 amino acids, was investigated. A sample was completely hydrolyzed into its constituent amino acids, and then that mixture was applied to a piece of chromatography paper and placed in a solvent. So we're looking at amino acids here. Suggest why only 4 spots were obtained in the chromatogram of the hydrolyzed pentapeptide. Well, if we're thinking about a pentapeptide, then we should really have 5 amino acids. But what this must mean is that 2 of the amino acids in the chain are the same. So there are only 4 different amino acids in the peptide, 2 are the same. That was maybe quite a kind of problem solving tricky question. It is known that the amino acid mixture contains the amino acid methionine. The RF value is 0.4. Draw a circle around the spot on the chromatogram which corresponds to that methionine. Well, there are 2 different kind of ways to do this. One of them is simply, if we think about it, take quite a logical approach and say, right, this is the distance that the solvent has moved. If you have a retention factor of 0.4, then that spot is going to be found just less than halfway up the distance that the paper has travelled. So if we look at that distance here, it can't be that dot at the top. It's not going to be the dot at the bottom. The dot at the kind of lower middle is just a wee bit too low. If we look at where the halfway line is, it's probably just here where I'm putting my mouse. So it's going to be the second dot down. Now, the way that you could do that, which makes it a little bit more accurate, is to use your ruler here. Measure the distance moved by the solvent, measure the distance of the different spots, and actually calculate the RF factors. Whichever RF factor you get, which is closest to 0.4, will probably be the correct answer. So the spot you're looking for here is the spot that's second from the top, and you can use either method to get that answer. So what we wanted to do today was be able to explain what chromatography is and what it can be used for. Hopefully this video was helpful in helping you achieve that. Calculate RF values for substances is very straightforward, and you are usually given the equation for this, so quite simple. Hopefully everybody can do that. And answer some problem solving questions. We will, of course, practice some more chromatography questions during the week once everybody has taken down the notes. But in the meantime, if you have any questions about anything, you can speak to your teacher on Google Classroom. Thanks for watching.